Good morning, good afternoon, and good evening, everybody. Welcome to Curing Reliability Issues at the IC Design Stage session, which is the first one from the Design for Manufacturing series. Further, I will use the acronym DFM for Design for Manufacturing. My name is Mario Sida, and I work at Mento Graphics as an European application engineer, supporting the analog mixed signal design and verification solutions. Together with Cyril Declev, the product marketing manager for AMS products, we have prepared this session for you. You may also register next Tuesday, November 16th, to the IP scoring using TSMC DFM Gates session, then on November 23rd to the session Sign-off Physical Verification in the place en route. The DFM Tech Talks dedicated to integrated circuits is then followed by 3 PCB-related technical talks between November 13th through December 14th. Today's session will last about 30 minutes. The presentation is followed by a Q&A part where Cyril will try to answer your questions. DFM is a collection of techniques to make integrated circuits more manufacturable. In other words, these are specific changes in the IC design process so that the functional yield, the parametric yield, and reliability will improve. In the pre-nanometer era, DFM consisted of a set of recommended design rules applied to the physical layout creation. In addition, worst case or corner case analysis was frequently used to verify the impact of process validations on performance and yield. With geometry scaling and advanced processes, integration becomes reality and engineers are able to create more complex applications. For instance, like short-range communication, Wi-Fi, Zigbee, mobile communication, GSM, WiMAX, LTE, high-speed I/Os like SerDes or transceivers, or last but not least, automotive control system, just to mention a few applications. As such, functional yield, parametric yield, and reliability are becoming dominant design challenges. Complexity of the system and the verification of design errors is one aspect. Sub-wavelength lithography leads to large spreads in timing and power for digital circuits and in performance for analog circuits. The extreme process variations, which affect transistor geometry and spatial variation in threshold voltage, is just another aspect. So, can it be manufactured? What is the cost of manufacturing? And what is the yield? Are 3 very important questions. DFM is not new, but as technology scales below 90 nanometers, 65, 45, 32 or 22 nanometers, it has a more significant impact on all the digital, analog or RF circuit design and manufacturing. Physical and quantum mechanical effects, previously not relevant, need to be modeled and may even become dominant. For instance, leakage currents are no longer neglectable. At smaller geometries, variability also gains in importance simply because same absolute tolerance becomes relatively larger when the absolute value of parameters decreases. For instance, a variation of the threshold voltage of 50 mV relative to a VTH of 200 mV is a much bigger problem than relative to a VTH of 700 mV. Technology scaling also means reducing the power supplies. That means architectures that once worked at 3.3 volts or 2.5 volts now need to work without any loss in performance at 1.2 volt, 1 volt or below. In addition, effects like shallow trench isolation induce stress, where NMOS transistors become slower and PMOS faster, or N-well proximity effects causes the MOSFET threshold voltages and other electrical characteristics to vary with the distance of the transistors to the well edge, and are also influencing the manufacturing cost and yield. As all these complex dependencies were not enough, there is also a time-dependent variation of parameters. Let's first view it from the user's perspective. Whether the end device is a portable phone, computer, a medical instrument, or a vehicle, the expectation is to be able to use it for a specific time, also called lifetime. Obviously, lifetime can differ a lot from one application area to another, as well as the impact of failure. Let's have a look to the failure rate over time. During the manufacturing, assembling, and testing process of the end device, the failure rate is decreasing very rapidly. Then the end device is ready to be used by customers and enters its intended lifetime, during which soft errors are mostly common. The normal lifetime is then followed by a wear-out period. During the wear-out phase, the failure rate is again increasing, and this is the main focus of today's session. As long as the failure would only show up after, say, 100 years, even for the automotive industry, this is well beyond the expected lifetime of the product. So it won't be not so much of a problem. The big issue is when these wear-out failures start happening at times that are completely comparable to the expected lifetime of the product. At smaller geometries, early wear-out effects are mainly caused by negative bias temperature instability and hot carrier injections. We will further use the abbreviations HCI and NBTI to refer to these two physical phenomena. Both effects induce interface changes in gate oxide, increase the threshold voltage, and reduce mobility. Consequently, they degrade transistor drive current, circuit speed, noise margin, and matching properties, which eventually will lead to partial or complete failure. So to seriously take these effects into account, they must be thoroughly modeled and considered at the design stage. Before we start to analyze the possible remedies of this problem, let's have a brief review of the physical effects. HCI is mostly affecting NMOS devices, while NBTI is mostly affecting PMOS devices. The lateral electric field accelerates carriers to sufficiently high energy so that they can cause impact ionization through collisions with the silicon lattice near the drain end. The initial electron-hole pair creation can cause further impact ionization, leading to an avalanche effect. The resulting mechanism is known as drain avalanche hot carrier injection. Depending on the operation condition, one or more hot carrier injection mechanisms can take place in a single transistor. The injected hot holes and electrons can cause oxide and interface damage, eventually leading to device failure. For NMOS devices, the threshold voltage typically increases due to the predominant electron trapping, and this increase, coupled with a mobility decrease, results in a smaller drain current. NBTI has received recently more attention because the PMOS device threshold voltage variation became the most limiting factor to design reliable CMOS circuits. NBTI is generally monitored by the degradation of the threshold voltage. This degradation strongly depends on the bias conditions and temperature. The mobility is also affected. Usually, at least threshold voltage and mobility degradations are modeled in any state-of-the-art NBTI model. Some models also consider dozens of other device model parameters, leading to very complex mathematical descriptions. Two main theories have been proposed to interpret NBTI degradation: reaction diffusion, or shortly RD, and hole trapping detrapping mechanism. The RD theory is the most accepted and explains the shift of the threshold voltage with the creation of traps at the interface between silicium and silicium dioxide in the presence of a strong vertical electrical field. These interface traps are generated by the dissociation of silicium-hydrogen bonds. Hydrogen comes from the oxidation. The released hydrogen then diffuses towards the gate. The creation of silicium plus interface states results in VTH increase. The whole process is amplified by high temperature by an exponential law. Reaction diffusion theory alone does not explain well the recovery mechanism, which we will describe on the next slide. Once the NBTI stress is removed from the device, a fraction of interface traps can self-anneal and the VTH degradation partially recovers. This recovery mechanism can be observed when a device is subject to a strain of stressing pulses. These conditions are called AC stress in the reliability community. During the first phase of the clock cycle, VTH increases due to the stress applied, and then it decreases again in the second half of the cycle. The general trend is still increasing because the recovery is only partial at each pulse. But the degradation rate is different, actually smaller, from the DC stress conditions when the device is permanently stressed. This has often led to the conclusion that AC stress is less problematic than DC stress. The degradation rate under AC stress conditions actually depends on the duty cycle of the applied stress signal. Historically, NBTI was studied in depth under pure NBTI condition, that is, considering devices under their normal on bias, which is a negative gate source voltage for a PMOS device. This was done without applying any drain source voltage. With other words, with zero lateral field and thus no current through the device. However, further in-depth studies have shown that the presence of a strong lateral field significantly modified the PMOS degradation characteristics. Researchers have also investigated a rising number of second-order effects, such as the impact of bulk biasing and the chosen layout geometries, like for instance in multi-finger structures heavily used for analog and RF applications. However, a widely accepted consensus for unified modeling is lacking, and many effects are still modeled with semi-empirical equations that fit experimental data. To conclude, the degradation profile should model both static and dynamic types of stress. Let's have a quick look to the circuit types affected by HCI and NBTI. Let's take a simple inverter gate. The upper figure shows the associated transfer characteristics plots versus time. The lower figure shows the output rising and falling propagation delay versus the aging period. It can be observed that T-fold delay depends on NMOS aging, is increasing quite a lot over time, therefore the HCI effects on the NMOS is predominant. Analog designs are also affected. Here we see how the transconduction gain in the bandpass and the dominant pole of an OTA are affected. Last but not least, RF circuits are also degrading over time. We see here how the phase noise of the VCO and the noise figure of the LNA are both shifted under NBTI stress, as presented in detail by a paper from the Beijing University. Whether the chip is primarily digital, analog or RF does not make much difference because the fundamental device behavior is affected. The problem, of course, has a different magnitude of consequences for a mission-critical device used in a medical application than for a disposable RFID. Intrinsic reliability lifetime of new technologies, CMOS 90 and newer technologies, are now on the order of expected product use times in the field. This is a quote from a major IC manufacturer for the automotive industry on aging. So far, we have been analyzing the causes and the symptoms of aging due to HCI and NBTI mainly. From now, we shall be looking at possible remedies. Assuming that do nothing and hope is not a viable solution, and you do want to take into account degradation due to HCI and NBTI at the design level, you may choose a conservative design approach. That means that all devices are considered to have much worse threshold voltage and mobility, and make sure that the design still functions. The degradation are derived from simple aging experiments conducted on a few pilot devices. By applying very high bias conditions and temperatures on a small sample, the degradation of threshold voltage and mobility are measured and extrapolated. Then these values are applied to all devices, and the design is expected to work properly in all corners. These measurements are usually done and provided by your selected foundry. Eventually, this kind of over-design translates into increased fabrication cost and does not take full advantage of the technology process. The reality is that during normal circuit operation, not all devices are equally stressed, and the amount of degradation highly depends on the exact dynamic bias conditions applied to the specific instance. So if this is the case, why not use it and apply this knowledge? The first generation of reliability simulation tools used aged models that were derived based solely on the age desired to estimate the performance of the circuit. Then degraded models were generated and the simulation repeated. However, the actual individual stress sustained by each device was not accurately taken into account. Also, the equations for the degradation process were hard-coded and simplistic. A second generation of reliability simulation tools has been developed and can be used with circuit simulators such as ELDO, ADIT and Questa ADMS. Each device experiences a different stress that depends on its exact individual bias conditions, in addition to global conditions such as temperature. This stress is computed individually. The resulting quantity is then used to determine degraded values of the model parameters as threshold, mobility, and using these degraded model parameters, a second simulation is run, which represents what would happen after n years of operation. In this age simulation, each device uses its own individual degraded model with updated values because the stress is device specific and so is the update. Fresh and age simulation results can be overlapped and compared. To further complicate an already difficult subject, aging appears to be a statistical process itself. If you consider two identical devices drawn side by side, they will have slightly different fresh threshold voltage, drive current and leakage currents. The distribution of these parameters is monitored by foundries, allowing statistical simulations by designers. The aging trajectories of two identical devices will be slightly different. That means devices that are matched at time zero may exhibit mismatch when they get old, with all the consequences on performance. Our simulators offer uniquely the possibility to assign statistical aging variations and simulate the resulting mismatch. A joint design reliability flow allows to predict the degradation of any metric, like oscillation frequency, power consumption, a distortion level, or a settling time. These metrics can be traced versus time and verified against the specification without the need to over-design. This example shows how the operating frequency of a CMOS oscillator degrades over time. The absolute period and the relative degradation in percentage of the frequency are shown in the upper and lower plots respectively. The x-axis is the time in years of logarithmic scale. The frequency is degraded by nearly 5% after 1 year of operation. The next thing a designer needs to know is which device is primarily responsible for the degradation of the observed metric. The simulator reports the devices that have their threshold voltage degraded the most severely, sorted by decreasing delta VTH. This allows to immediately identify the sensitive part of the circuit and make the design robust against aging. Aging of a specific block or macro, whether it is an RF or analog block, may need to be simulated together with surrounding circuitry. With ELDO, the designers are able to selectively include or exclude parts of the circuit from the aging analysis. As circuit size increases, one may need to use a fast-spice engine like ADIT to accommodate the size and at the same time analyze the aging of a critical portion of the design. Eventually, the design might contain parts described in analog or digital hardware description languages, which need to be incorporated into the simulation to configure a specific operation mode or describe a specific function. Test scenarios often are described with System C or System Verilog languages. ELDO, ADIT and Questa ADMS are helping you to manage the complexity. With this, we came to the end of the presentation. Thank you for your attention. We will now continue with the question and answer part.